Hello, welcome back. So this is part 2 of chapter 23. We were talking about this example of car dealers, and we're trying to predict the price of a used car is a 3-year-old Toyota Camry. The dependent variable will be the price, and the independent variable will be the mileage on the car. And price is measured in $1,000, mileage is measured in thousands. All right. So next, I would like to show you how we can run the regression using Excel. So let me switch over to Excel. Okay, so right now, you should see Excel spreadsheet with 3 columns up here: price, odometer, and color. Okay, so this is the data for our example. What we want to do right now is to run a simple linear regression using price and odometer. So what you're going to do is you go to data, click on data analysis. Then you will see this little window showing up. And you want to choose regression right here. Click OK. And highlight the Y range and X range. And you need to make sure you don't reverse these two. So our Y is the dependent variable, which is the price. So you're going to highlight price. X is the independent variable, which is odometer reading in our example. Okay. And since I included labels in the first row, so I want to click on the labels. Usually I do change the upper range so I can see the result within the same spreadsheet, but you can leave it as the default, a new spreadsheet. So right now everything is okay for our purpose. So just click on OK, you will see the output. All right. So that's the output for our simple linear regression using Excel. Okay, we're gonna talk about how to read the output and what information can we derive from it. So let's switch back to the PowerPoint. Okay, so just to let you know, in case you forget how we run the regression, here's the pop-up window that you need to set up in order to run the regression. And then once you click OK, you will see the results shown here. Right. So with the results, the first thing we can do is write out the regression equation, because now we have the estimate for alpha and beta, right? So we're going to start from the bottom line here. If you see the coefficients, this column gives us the estimate for our alpha and beta, so which is denoted by A and B in the regression estimates. So there's a typo. Let me fix that. Okay, so the y-intercept is estimated to be 17.25. And the slope coefficient is estimated to be negative 0.0669. With these two numbers, we can write out our regression line as y hat equal to 17.25 minus 0.0669x. Okay, and there was a typo here. It should be 17.25. All right. Now, before we can use the regression to do forecasting or other uses, we need to check a few things. Okay. So what do we look at? Now, the first one is our slope coefficients. It's more important than the y-intercept. Okay, and actually, most of the time when we estimate a simple linear regression, we do want to find out the relationship between x and y, and therefore the slope coefficient is the key. It's the key connection between these two variables. So for our example here, the slope coefficient turns to be negative 0.0669. What does it imply? Or how do we interpret that? Well, since it's negative, first of all, we can tell that x, y, and are negatively related, which makes sense because typically the higher the mileage, the lower the price of a used car, right? But what exactly do we find? We find that for each additional mile on the odometer, the price will increase by 6.69 cents. And notice that although the number is 0.0669, since price is measured in $1,000, when we interpret that, we need to multiply this number by 1,000 to convert it back to dollars. And that's why we can say for each additional mile on the odometer, price will decrease by 6.69 cents. So that's how we interpret the slope coefficient. Now for the y-intercept, we find it to be 17.25, or if you convert it back to dollars, it's $1,750. Can we say, well, typically for y-intercept, we'll say if the value of y when x is equal to 0. But can we say that when there's 0 mileage on the car, the selling price is around $1,700? It may sound reasonable to a certain extent, because if you think about a new Toyota Camry, it's around $1,700. However, the issue here is that number one, 0 is not in our data, okay? Because we're talking about used cars, and it doesn't make sense for a car to have 0 mileage when it is used. Even for new cars, it won't be 0 mileage. So second, it doesn't make sense for x to be 0 because no car has 0 mileage. Of course, every car has 0 mileage at the beginning, but they usually test drive the car before sending it out from the factory. And therefore, although it seems like we can interpret the y-intercept, it turns out we won't be able to, at least for our regression analysis. Okay, so most of the time for simple linear regression, there's no interpretation for the y-intercept, especially when x equal to 0 is not included in our data, right? So that's the first thing we check. We look at the coefficient. Now the second thing we check is we test the slope, okay? We conduct hypothesis test on the slope. We mentioned this before. We mentioned hypothesis test briefly before, and here we're gonna use what you learned in hypothesis test to test the slope, okay? When we talk about hypothesis test, we didn't go very far, we didn't talk in details, but one thing I emphasize there is that you can use p-value, you can look at p-value to test hypothesis. So that's what we're gonna do here. And the question is, why do we test the slope? So here's the reason. As I mentioned, the slope coefficient is the key connection between the two variables. And since our interest is the relationship between the two variables, we want to make sure that the connection, the key connection between these two variables are in fact true or in fact exist. And therefore, we test on the beta, okay? It depends on beta 1. Now think about it. When beta 1 is equal to 0, okay? Let me write it. So we have y equal to beta 0 plus beta 1x plus the error term as our regression line. This is our original simple linear regression model, right? If beta 1 is equal to 0, what will happen? Well, if beta 1 is equal to 0, then x will be dropped from the model together with beta 1 because 0 times x will be equal to 0. And if x is dropped from the model, then what we would observe is that y is not related to x at all. Y is just equal to beta 0 plus an error term. In that sense, it's actually it doesn't make sense for us to estimate a regression model in the first place because there's no relationship between these two variables. So that's the situation we want to exclude, Or in other words, that's the situation we want to verify that does not exist in our regression analysis. And this is the reason why we test on beta 1 to make sure that beta 1 is different from 0. So our purpose here is really to try to find evidence in support of the alternative. So what kind of evidence are we looking for? Well, as I mentioned before, we're going to look at the p-value. And p-value likely is reported in our output. Okay, this is part of the output we have from Excel. And along the row for odometer, if you go to the very last column, p-value, you will find out that the p-value is equal to 0, which means good news for us, because the criteria is that if p-value is less than alpha, our significance level, we're gonna reject the null hypothesis. Okay, and that means we can claim that beta 1 is different from 0. Once we reject the null hypothesis, back here, once we can reject the null hypothesis, we can claim that the alternative is supported, and therefore we can say beta 1 is different from 0. And that means it does make sense for us to estimate a simple linear regression model for these two variables because they are correlated. Okay? So in the future, you run a simple linear regression model, then the next thing you check is to look at the p-value for the slope coefficient to make sure it is significant. Or in other words, to make sure this p-value is small enough, smaller than alpha level. Alpha could be, by the way, if you forgot, alpha could be 1%, 5%, or 10%. Okay, so let's test on the slope. The next thing we can do, sometimes we not only want to know that x, y are correlated, we also want to verify whether they're positive related or negative related. And we call those one-tailed tests. Now, just a quick tour for you here. If we are interested in the sign of the slope coefficient, which is called the one-tailed test, all we do is really to divide the p-value by 2. The p-value is reported in Excel, we'll divide that by 2. We've got the new p-value for the one-tailed test, and that's really all you need to do. Okay. All right. So now we'll verify x and y are correlated. Next step is to check how well the model fits the data. Okay. So you have the data, you can estimate model, but sometimes model is good for the data, therefore your prediction will be good. And sometimes the model is lousy, it doesn't fit the data well, and then your prediction will be quite off. In that situation, when your prediction is quite off, as you can imagine, if you're using this to make your business decisions, your decision will run into a big risk of wrong decision. You will run into a big risk of making the wrong decision. Okay, so how do we check that? There's a measure called Rsquared, which is also reported in Excel right here on the top. So let me switch all the way back just to highlight here. Okay, this is the overall Excel output, and Rsquared is reported in line 1 in our case here. So Rsquared is equal to 0.6483. What does it mean? Okay. So R-squared actually tells us the proportion of variance in Y that is explained by X. Okay, it measures the strength of the relationship. All right. So here's the basic idea. When we estimate the model, we're trying to explain in a sense that when mileage changes, price will change with it. That's our logic, and that's why we can estimate this regression model. And in a sense, if we can claim that most of the variation in price is due to the variation in mileage, that means mileage is a very important factor for explaining the variation in price. So in that sense, we can measure how much variance in price can be explained by the variation in X. the odometer reading, then we can claim if most of the variation can be explained, we can claim the model is a good fit. Okay? So for our R-square here, 64%, is it good or bad? Well, the downside of R-squared is that there's no critical value or there's no threshold that will enable us to draw the conclusions. We won't be able to say, oh, R-squared higher than this is good, R-squared lower than that is bad. The only thing we can say is the higher the R-squared, the better. Okay, so R-squared equal to 0 is the perfect match, which potentially also means there's no need for regression analysis. R-squared equal to 0, that means there's no relationship between x and y, and there's no need for regression either. So we usually look for R-squared in between 1 and 0, and R-squared will be between 1 and 0 most of the time. Okay. And then for our 64.8%, I would say that's relatively a good R-squared, and this is also based on experience. Actually, the kind of interpretation whether R-squared is high enough or not is more relying on a person's experience with regression analysis. The more regression analysis you do, the more experience and the better idea you would have. Okay? Now, interpretation for the R-squared, we're going to say, for this example, 64.8% of the variation in the selling price is explained by the variation in the mileage. Okay? And the more the better, so 64 is roughly a good number. So that's all we have for chapter 23, the simple linear regression. So talk to you next time.